This next lesson is the whole point of this chapter, which is basically to take a function and to make it into an infinite series. There are so many things that you can do with a function when it is expressed as an infinite series than otherwise. And also to find where that series is good. Meaning, where is it truly valid? Where does it actually approximate or, in some cases, equal the original function? We know that a geometric series has a formula of s is equal to the first term over 1 minus the common ratio for a common ratio less than 1, which basically means that a common ratio is, or absolute value, which means that that common ratio, that r value, is contained within the interval of 0 to 1. So if we extrapolate that to a function like f of x is equal to 1 over 1 minus x, we can say that that is equal to a polynomial, which is the sum from n equals 0 to infinity of x to the nth power, but also only for x contained within that same interval that r would be, which is what this really is. I mean, if I have this centered at x equals 0, I can say that the function 1 over 1 minus x is equal to, well, the first term of this would be 1, then you'd add an x, then you'd add an x squared, then an x cubed, and so on. And this would be true for x contained within -1 to 1. So I want to open Desmos up and take a look at what this looks like from a graphing calculator standpoint and see if this is truly an approximation, because this is an immensely powerful result that we can extend to many other functions. So let's graph f of x is equal to 1 over 1 minus x, which is just a shifting of a 1 over x function. So you can see that's a hyperbola of types that we've done before. Then I want to graph f of x is equal to 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th. And as I zoom in on this region between 0 and 1, which will be made easier by graphing x equals, let's do -1 to 1, sorry, -1 and x equals 1. I'm going to make both of these be dotted lines so we can see what they really look like. So this is the region, or what I would call the interval of convergence. This is where this function is truly getting to be exactly like that. And let's stick in a few more terms just to be very clear about what's happening. So x to the 6th plus x to the 7th plus x to the 8th. Every successive term makes that blue line match the red line more and more and more. But it won't occur outside the interval of -1 to 1. That is the interval of convergence, and it doesn't include -1 and 1 because in a classic geometric sequence, the endpoints of -1 to 1 do not form a geometric sequence. So let's look at what you're actually going to be doing with this information. Let's take a function like h of x is equal to 1 over 1 minus x squared. So this is a different kind of function, but my goal is to take this function and to match it with a of 1 over 1 minus r. Think of this as your matching game. So when you do that, you can say that my first term, a of 1, is 1. That's the numerator. And my common ratio, r, is equal to x squared. And also, in order to converge, I need the absolute value of x squared to be less than 1. That's what has to happen because we know that in a geometric series, the absolute value of r needs to be less than 1 in order for that series to converge. Well, the absolute value of x squared less than or equal to 1 is actually going to give the same convergence pattern as -1 to 1. And you can kind of substitute values in and see that that would be true. Those are the only values that would end up working. So then we take this and we match it to the sigma we did before, the sum from n equals 0 to infinity of, so we have 1 times r raised to the nth power. And by convention, we don't do raised to the n minus 1 because we start with an n equals 0. It's a lot easier to do it this way. So this right here is the a sub 1 value, and this is the r value. And when I simplify that, I get the sum from n equals 0 to infinity of x to the 2n. And again, this is only on -1 to 1. Now, we always want to be very clear about these endpoints. So we are going to check the endpoint of -1, meaning I'm actually going to sub -1 in for x, which gives me the sum from n equals 0 to infinity of -1 to the 2n. Well, -1 to the 2n is just an infinite number of 1s, because raising something to the 2n is going to make -1 be positive. So I get 1 plus 1 plus 1 plus 1. That clearly diverges, so the endpoint of -1 doesn't work. Now let's check 1. If I substitute 1 in, I get 1 to the 2n, which is also 1 plus 1 plus 1, etc. So that also diverges. So I know that my endpoints don't work, and the power series representation of 1 over 1 minus x squared is this, but only within that interval of convergence. It is not enough to know what the power series representation of a function is. You have to know what the interval of convergence is to know where it is actually good. For what x values does it truly represent the same thing? This is why we did all that series convergence testing in the first 2/3 of the chapter. Okay, let's try another one. H of x is equal to x over 1 minus x. This is another rational function. And if I look and compare it with that same a sub 1 over 1 minus r, I see that a sub 1 is equal to x and r is equal to x. So furthermore, because r is equal to x, I know that the absolute value of x has to be less than 1, which means that same x is contained within the open interval -1 to 1. So that's not a shock there. Then a couple of things I can look at with this. The first is I can just treat this as a sub 1 is x. So my first term is, let's see, my first term would be x. Then my next term would be multiplied by x, so x squared, then x cubed, and then so forth. I could also treat this as x times 1 over 1 minus x, which I've already done this one. So since this is x times 1 over 1 minus x, this would be x over 1 plus x squared plus x cubed, and so forth. And it gives me the same thing. Hey, we just got the notice that school will be closed. I guess I'm glad I'm recording this right now. Okay, so continuing on, either one of these lets us know that this sequence is going to be represented by this thing. So your job now is just to take that and represent it as a sigma. The sum from n equals, I'm going to pause there and just put an x to the n, because that's the simplest way. But you'll note that my first term is actually an x, so I can just say n equals 1 to infinity of x to the n. And this would be for x contained within the open interval -1 to 1. So that gets me that one, and it's basically the same thing as we just did right up here. It's the same thing as this one. However, my n value is starting at 1 instead of 0 to account for the fact that we're losing a term. We're losing this term right here. Okay, next, h of x is equal to 1 over 2 minus x. This is a little bit different, so I have to do some algebra to manipulate this to become like the form that we need it to be, a sub 1 over 1 minus r. This 1 is non-negotiable. It needs to be a 1. It is a 2 right now, but that's okay. We can divide the numerator and denominator of this rational expression by a2, which means multiplying it both by a 1/2. And if you want to see it like that, I can say times 1/2 times 1/2, which gives me a 1/2 over 1 minus x over 2. So that's the same expression done, but Alexa, timer off. But now I'm going to get a
40-minute timer stopped on
a sub 1 equals 1 over 2 I get an R value of x over 2. You can kind of play the matching game that this goes to that, and this goes to that. We can even now build our sequence because the first term is 1/2. The second term would be 1/2 times r. So we multiply it by r, I get x over 4. Then I multiply it by another r, I get x squared over 8, and so forth. You can see how the pattern's going. But my sigma is going to be the sum from n equals, we can put in a 0 to infinity, first term times r to the nth power. We can also express that as the sum from n equals 0 to infinity of x to the n over, this would be 2 to the n times another 2, it would be 2 to the n plus 1, if you want to treat that as coefficients and, coefficients and the actual terms. But let's kind of make sure that we know that this thing also has to be absolute value less than 1. So my common ratio has to be less than 1. So we're going to actually test that. My common ratio has to be less than, that means that has to be between -1 and 1, which when I multiply by 2 gives me -2 to 2. So this is truly between -2 and 2. And if I plug -2 back in, and if I plug 2 in, I'm going to see that the whole thing diverges. For the same reason that I did up above. It's just going to be constant plus constant plus constant. You can test that yourself. But this is my answer right here. And it's going to be on x is an element of -2 to 2. So that is the whole thing that we have for this. Okay, next example, number 4. We're looking at a function that is going to be a slight variation of this 1 over 1 plus x. Now, many of you have experience with knowing that 1 over 1 plus x can be rewritten as 1 over 1 minus a negative x. This now will make it fully match the form. So we did this with arctangent. We did a little bit of a matching game where we had to make our function look like a particular form. I find it helpful to just call a1 is equal to 1 and r is equal to negative x. This is a good reminder to yourself that you know what you're doing and you know why you're doing it. And it's also a reminder to the grader or the reader, whether that's me or an AP person, that you know what you're doing. Then we can write the sum from n equals 0 to infinity of negative x raised to the nth power, which we can then rewrite in a better alternating form by pulling that -1 to the n out as -1 to the n x to the n. This very clearly identifies this as an alternating series. Furthermore, when it comes to our testing for our convergence, our radius of convergence, we know that the absolute value of negative x has to be less than 1, which is the same as the absolute value of x is less than 1, which is the same as our x must be contained within the interval of -1 to 1. But like before, we need to test our endpoints. This is always going to be a key thing of this, is that we must test our endpoints to see if the sequence converges or diverges at those particular endpoints. So we're going to test -1 to see what our interval of convergence does there. So if I plug -1 in, I get the sum from n equals 0 to infinity of, okay, sorry about that, of so the sum from n equals 0 to infinity of -1 to the n, and plugging -1 in, I get another -1 to the n. And this simplifies to give me, well, since it's -1 both to the n, that is the same as 1 to the n, which very clearly diverges. I mean, at this point, we don't need to say that that's just a sum of infinite numbers of 1s. Then if I test 1, the other endpoint, I get the sum from n equals 0 to infinity of -1 to the nth power and 1 to the nth power, which just gives me an infinite number of -1s being added up, because that goes away, and all I'm going to have is just -1 plus -1 plus -1. That also diverges. So we can very, very safely conclude that that is our interval of convergence. Remember, the radius of convergence, radius is 1, but the interval of convergence, we test the endpoints to make sure that that's our true interval. Okay, 2 more examples. let's do a sum of 2. So 1 over 1 minus x plus 1 over 1 plus x. If you have a sum, I would advise adding them up to become a single rational expression rather than do some sort of sum of two different sequences. This is going to be far easier. So I know that if I add them with the least common denominator, I get 1 plus x plus 1 minus x over the quantity 1 minus x squared. Or better yet, I get 2 over 1 minus x squared, which then can be simplified to kind of express that this is just a let's see, this is an a sub 1 of 2 and an r of x squared. So then my sigma is going to be the sum from n equals 0 to infinity of 2 times x to the 2 to the n, or x to the 2n. Now, a fun little thing to do is actually to verify that if I were to just treat those as two different sequences, my first one would be the sum from n equals 0 to infinity of, let's see, that'd be 1 times x to the n, and then we'd have plus the sum from n equals 0 to infinity of negative 1 to the n, x to the n for the second one. We've actually already done the two of those earlier. So in the first case, if I add them, I get 1 plus x squared plus x cubed, and so on. And in the second case, if I add them, I get 1, let's see, 0. So I plug 0 in, I get 1. Then I get minus x plus x squared minus x cubed plus x to the 4th. It's like all of my odd powers cancel. So I basically get 2 of the 1 plus x squareds plus x to the 4ths, and so on. And that is the same thing as what this is doing. So it's kind of a nice way to just express this. Okay. Lastly, we're going to look at differentiation and integration, because one of the big purposes of this is that it takes things that are very difficult to differentiate and integrate and changes them into polynomials, which we have a better perspective on how to do those, especially the properties with polynomials make it much cleaner. So let's say that I have a polynomial equal to a function that's equal to a sigma, a sum from n equals 0 to infinity of sum a sub n times x minus c to the n, just a basic power series. So remember, with a power series, you have a coefficient and you have a term. And this term is centered at c, so just kind of writing some properties down from before. And if I write the terms out of this particular sequence, what I get is that this is equal to a sub 1 plus, not a sub 1, a sub 0 plus a sub 1 times x minus c plus a sub 2 times an x minus c squared, and so on. Well, let's examine a derivative of this. In other words, let's examine what an f prime of this would look like. So if I looked, sorry, this is being a little weird. If I looked at an f prime, what I would get is that f prime of x would be equal to, the derivative of a sub 0 is 0. The derivative of a sub 1 x minus c would just be a sub 1. Then I have 2 a sub 2 times an x minus c to the first power, plus then I would have 3 a sub 3 x minus c to the second power, and so on. I could summarize that by saying that I have the sum from n equals 0 to infinity of n a sub n x minus c to the n minus 1. Seems complicated, but again, you can go from here, this original series, directly to here. That's kind of the definition of power rule back when we first learned derivation over a year ago. So one leads directly into the other. And likewise, I have the integral of f of x dx is equal to the sum, and if I do power rule the other way, then I raise to the n plus 1 and divide it by n plus 1. So I get a sub n x minus c to the n plus 1 over n plus 1 plus a constant of integration. The thing that I need you to remember and know about this is that the radius of convergence is the same, but the endpoints for the interval of convergence, the endpoints need to be retested. You need to retest your endpoints anytime you integrate or take a derivative. So let's look at another example now. H of x is equal to 1 over 2 minus x squared. And if I do this, then I can kind of, well, this is a weird one to try to write as a series. It's not very clean. It definitely doesn't match the form that we need to. And what I need to ask myself is, would an integral or a derivative make this better? Would an integral or derivative make this better? A derivative reduces the power, but it increases the power of the denominator. An integral decreases the power of the denominator. So if I do an integral of this, let's do an integral of 1 over 2 minus x squared dx, which, okay, so the fact that it's 2 minus x squared means it's the same thing as x minus 2 squared, since that's an even function property, or just think of factoring a negative 1 out and squaring it. We get this, which is the same as x minus 2 to the negative 2 dx. Remember, no u substitution needed there. And if I integrate that, I get negative x minus 2 to the negative 1 plus a constant. Or, better yet, I get 1 over 2 minus x plus a constant if I pull that negative 1 back in. Okay, this is something, this 1 over 2 minus x is something that we can make a power rule of, or a power series of. I can do that relatively easily by rewriting it as, okay, divide by a 2, I get 1/2 over 1 minus x over 2, which is now the same thing as the sum from n equals 0 to infinity of a 1/2 times an x over 2 to the nth power. And we still have a plus a constant of integration. I think it's important that that plus c be present in everything. So this is the integral of what I wanted. So note how that plus c is just kind of hanging out, but if this is the integral of what I wanted, then we're just going to go ahead and do its derivative. And we're going to do that using basic power rule. I get the sum from n equals 0 to infinity of n over 2 times x over 2 raised to the n minus 1. And that's it. That is my derivative. So we need to look back at the original and kind of come up with what our interval of convergence would be. So I'm going to look way back up here when we first defined this power series, and let's kind of pull it from here. We know that the, let's see, I know that, oh no, not here. We want it to be right here. I know that x over 2 absolute value has to be less than 1, which means that x is going to be in between negative 2 and 2. And if I go back to my other one, we want to test negative 2. So if I plug negative 2 in for x, what I get is the sum from n equals 0 to infinity of n over 2 times a negative 2 over 2, so that's negative 1 to the n minus 1. That just means it's going to be alternating. But let's treat this and start pulling some different properties out. So if I pull the 1/2 out, because it's a constant multiplier, I get the sum from n equals 0 to infinity of a negative 1 to the n minus 1 n. Well, that's going to be 1/2 times, so if we just kind of plug that in, it's going to be 1/2 times a 1 minus 1 plus 1 minus 1. That does not converge, that diverges, because its sequence of partial sums does not converge. I know it seems like the sum would be 0 or 1 or negative 1, depending on how you group your terms, but with the ambiguity and uncertainty, you have to say that that diverges. Then we're going to test 2. The sum from n equals 0 to infinity of n over 2 times 1 to the n minus 1, which might as well just cancel out. And this very clearly diverges, because that's just going to be if I factor the 1/2 out, that's just the sequence of 1 plus 2 plus 3 plus 4 plus 5. And actually, that's same with this. Sorry, I messed that one up. This is just going to be the sequence of 1 minus 2 plus 3 minus 4 plus 5, and so forth. That still diverges. It just grows, grows, and grows. Okay. So bottom line is, with all these, you have to test your interval of convergence. So our final answer for this would be that it's kind of worth going back up to see what we did. We can say that this 1 over 2 minus x squared is equal to this sum from n equals 0 to infinity of n over 2 times x over 2 to the n minus 1, but only for x between -2 and 2, because we've checked the endpoints. So that's a power series for that one. Okay. Let's call this one 7a. H of x is equal to 1 over 1 plus x squared, which if I rewrite this is the same as 1 over 1 minus a negative x squared. And I'm just going to kind of use this to establish a series for this one. I know that that's going to be equal to the sum from n equals 0 to infinity of a negative x squared to the nth power. And if I pull out the -1 to the n, I'm going to get a -1 to the n x to the 2n. So what I'm establishing is that this is equal to this 1 over 1 plus x squared. And we'll kind of hang on for the interval and radius of convergence of that one for a second. And let's go to this next one, 7b. The real meat of this is looking at f of x is equal to the arctangent of x. And I want to derive what a power series for this would be. I do know that the derivative of arctangent is 1 over 1 plus x squared, which happens to not so coincidentally be the sequence that we did, or the series we did right up above. This one. So how do we relate the two of them? Well, the arctangent of x is equal to the integral of 1 over 1 plus x squared, which should be the integral of this power series, the sum from n equals 0 to infinity of -1 to the n x to the 2n dx, which is equal to the sum from n equals 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1 plus a constant. To find what that constant is, we want to plug in, well, we can plug in 0 for x. We're going to plug in x equals 0. I know that the arctangent of 0 is 0. So if I plug into 0 to both sides, what I basically get is that c has to be equal to 0. So that means that this goes away, and I know that my series is this. -1 to the n, x to the 2n plus 1 over 2n plus 1. Now I'm going to go back up and examine the interval and radius of convergence. I know that this, the r value is equal to -x squared, which means that that -x squared had to be less than 1, which again means that x is in between -1 and 1. So we have a radius of convergence of 1. So knowing that, sorry, I'm going to say radius equals 1. I want to go ahead and I want to test -1 and I want to test 1. I need to test my endpoints. So we're going to test -1 and I'm going to plug -1 in. I get the sum from n equals 0 to infinity of -1 to the n times -1 to the 2n plus 1 over 2n plus 1. This takes some good mathematics to figure out what's happening with this. What I know is that this is the same as the sum from n equals 0 to infinity of -1 to the 3n plus 1 over 2n plus 1. So raising to the 3n plus 1 is going to basically have the effect of, well, if I plug n equals 0, I get 1. If I plug n equals 2, I get, let's let's see, or sorry, n equals 1, I get an even. It's going to alternate between even, odd. And because the denominator is growing, what we can say very, very safely is that this converges by the alternating series convergence test. It is alternating. You want to be very careful and clear that it is alternating. So again, as you plug in values, this alternates positive, negative, and this grows. Remember the nth term test is part of the alternating series convergence test. Oops. Now finally we're going to test 1. I get the sum from n equals 0 to infinity of, I have negative 1 to the n, 1 to the 2n plus 1 over 2n plus 1. Well, that 1 to the 2n plus 1 goes away. And what I basically get is negative 1 to the n. Negative 1 to the n is also going to alternate. As n increases, it's going to go positive, negative. So I could say, is this also converges by alternating series convergence test? So the interval is x is contained within negative 1. Sorry, this tip is coming apart. X is contained within negative 1 to 1. And that's it.